In the last video we looked at this example here and we saw that it's not an exact differential equation. We cannot write the left hand side as the derivative with respect to x of some product. That was the last example we did in the previous video. However, if we multiply both sides by x, then we can write the left hand side as the derivative of a product with respect to x. So we have an x cubed here and its derivative is 3x squared, whereas up here the derivative of x squared is 2x, but we had a 3 here. So we can't write this as the derivative of a product. We went on to solve this differential equation. Straightforward once you find out what the left hand side is. Now the function that we multiplied our differential equation by in order to make it exact is called the integrating factor. So the integrating factor in this example is x. Let's take a look at some more differential equations, and here we want to see which of the following of them can be made exact by multiplying by x squared. So let's look at some solutions. Let's take this first one and multiply it by x squared. Well, we get x squared dy dx, x squared by 2 over x is 2x, and we get 4x squared on the right hand side. So all we want is that the function of x in front of dy dx has a derivative which is in front of y. The derivative of x squared is 2x. So that means we can write the left hand side as the derivative with respect to x of this function x squared times y. If we multiply this one by x squared, we can make this second equation exact, because the derivative of x cubed is 3x squared, so we can write it, the left hand side is the derivative of x cubed times y. The product rule then will give us the left hand side. What about this one here? If we multiply by x squared, we get x dy dx minus 1y equals x. Let's take a closer look at this one. Multiply everything by x squared. So we get x dy dx minus y equals x cubed. So why is this not exact? Well, the problem is the minus sign. Okay, the derivative of x is 1, but it's not minus 1. If we differentiate xy with respect to x, we get x dy dx plus y times 1. Okay, x times the derivative of y with respect to x plus y times the derivative of x with respect to x. So it's the minus sign here is a problem. However, this equation is already exact. The derivative of 1 over x is actually minus 1 over x squared. 1 over x is x to the minus 1. So we get minus x to the minus 2, which can be written as minus 1 over x squared. So we can write the left hand side as the derivative with respect to x of the function of x in front of dy dx, which is 1 over x times y. So d dx of 1 over x is minus 1 over x squared times y, that's that term there, plus 1 over x times dy dx. So this equation as it stands is exact. The next equation is not exact because the derivative of 1 over x is minus 1 over x squared, and we have a plus 1 over x squared here. If we multiply all of this equation by x squared, we'll get x dy dx plus y equals 3. And we can see here that the derivative of x is plus 1. So we can write the left hand side here as the derivative of xy with respect to x. Next we will see how to find the integrating factor for a linear ordinary differential equation. So here we have an equation governing the current I in a circuit with inductance L and resistance R. The electromotive force is E cos omega t. So E omega L and R are constants. So the dependent variable is I, the independent variable is t. Now this equation is linear because the dependent variable I is not raised to any power. We just have linear terms in I, like a constant times I. And also derivatives of I with respect to time appear as linear terms. We just have derivatives times constants. We don't have the derivative raised to a power, or di dt, the derivative multiplied by I. We don't have nonlinear terms like that. Of course, the independent variable t doesn't appear as a linear term. It's the argument of a cos function, but that's okay because t is the independent variable. Now, in general, a linear first order ordinary differential equation is written like this. So here, y is the dependent variable. Sorry, x is the independent variable. So we write the derivative first. Then we have the dependent variable term, but in front of it we just have a constant or a function of the independent variable, and on the right hand side we have a constant or a function of the independent variable. So again, because it's linear, we don't have dy dx raised to a power, we don't have y raised to a power, we don't have y multiplied by a derivative or anything like that. We can multiply y by a constant or by a function of x, that's allowed. Also, y doesn't appear as the argument of some function like cos or sine. We just have linear terms in y. We can consider a function of x times y to be a linear term in y, as long as we don't have a function of y times y. Now let's write our differential equation for an LR circuit in this standard form. So we just have to divide across by L. So here's the general situation actually. We just replace y with I and x with t. So anyway, dividing across by L, we get this. Here we will go through the method for getting the integrating factor for this differential equation. We integrate the coefficient of the dependent variable here. So the dependent variable is I, so we integrate R over L with respect to the independent variable, which is t. And since R over L is just a constant, we get R over L times t. Next, we raise e to the power of this here, e to the power of RT over L. That's our integrating factor. So here is the general picture of our first order linear differential equation. The integrating factor is got by integrating the coefficient of y. Well, we can call it the coefficient of y. It doesn't have to be a constant. It could be any function of the independent variable, x in this case. We integrate it with respect to x and then we take the exponential of it. Let's get the integrating factor for this differential equation here. Now first of all, we have to get the derivative on its own, so we need to divide across by x. So we get dy dx plus 2y equals e to the minus 2x. So that's what we have here. And then we look at the coefficient here of the dependent variable y. We integrate it with respect to the independent variable, which is x, to get 2x, and we take the exponential of it. So the integrating factor is e to the 2x. Now at last we're ready to solve equations using the integrating factor. Let's go back to the equation for the LR circuit, and the integrating factor was e to the power of the integral of R over L with respect to time. So that was e to the RT over L, as we saw. So what did we do with an integrating factor? Well, to make our equation exact, we multiply it by the integrating factor. So we multiply this by e to the RT over L. So now the left hand side should be writable as the derivative of a product of functions with respect to time. And as we saw in the previous video, the functions in the product are the function in front of this derivative, e to the RT over L, and the dependent variable, which is I. So the left hand side is the derivative of the integrating factor multiplied by the dependent variable. That's always the case. So we could have just went straight from here down to here, just put the integrating factor times I, differentiated with respect to time, and then multiply the integrating factor by the right hand side. And as we saw in the previous video, then we can multiply both sides here by dt and then integrate both sides. So we'd integrate d of what's in here to just get it back, and then we integrate the right hand side with respect to time. E over L is a constant, so we can take out that, and we have to use integration by parts here because we have an exponential term which is a function of t, and we have a trigonometric term, a function of t. Let's just go through this integration. We use the rule LIATE to decide which function we call u in our formula for integration by parts. So the exponential term is this one here, e to the power of RT over L, and the trigonometric term is cos omega t. So the t comes before e in this rule, so we let u equal cos omega t. We've got to differentiate this, so du dt is the derivative of cos is minus sine, and then we have to multiply by the derivative of the angle with respect to time, which is omega. So we get minus omega sine omega t, and multiply both sides by dt. So if u is cos omega t, then dv is e to the RT over L times dt. So integrating here, so we differentiated the cos function, we integrate the exponential function. If we integrate the exponential function, we get it back. But then we must divide by the coefficient of t, divide by r over L. That's the same as multiplying by L over r. Okay, so we plug in for u and v. U is cos omega t, there's v, and we have to integrate v with respect to u. So here's v. Well, we have to multiply v by du. So here's du, minus omega appears in it, so I take out the minus omega, so we'll have a plus omega here. Unfortunately, as you can see, we have to do another integration by parts. So let's just quickly go through that. We let u equal a trigonometric term like we did here. So in this case, u is sine omega t. So du, the derivative of sine is cos, and we have to multiply by the derivative of the angle, which is omega. dv then is what's left, e to the RT over L times dt. So v is going to be just like before, L over r, e to the RT over L. So here's what we get: u times v, minus the integral of v times du, v times du. L over r times omega can come out, and we have a dt here, so dt here. Now you can see that this integral here is the same as our original problem, this up here. So I'll just call our original problem I. So this integral is called I. So now I, our original problem, is given by this here. So I've just copied this down here, and we've omega L over r times this. Well, this is what we have down here. So I've written L over r times sine omega t times the exponential term. Then we've minus L omega over r times this here, which is I, of course. So we have to solve this for I, so we need to combine the I terms. So we have this I on the left hand side, and we have to bring over this one, so we have omega L over r times minus omega L over r. That's minus omega squared L squared over r squared, and bring it over. Plus omega squared L squared over r squared times I. So we can factorize I out of this. and that must give us what's left. So what's left is this term here and this term here, but we can take L over R out, and we can also take the exponential term out. Then inside the bracket here we have cos omega t for this term, and for this term here, well, we've taken out L over R and the exponential term, and we're left with omega L over R times sine omega t. Okay, now we need to find I. So what we can do is multiply everything here by R squared. So inside the bracket here we get R squared plus omega squared L squared. So that's where this denominator comes from actually. And if we multiply the right hand side by R squared, we'll get LR into this bracket here. Well, we can leave the L out as was done up here for the numerator. But we can take the R in, so we'll get R cos omega t, that's that term there, and R times this term will give us omega L. So multiplying this by R squared means cancelling this R here, and multiplying in here by R. So we cancel this R here, and over here when we multiply by R squared we get an R squared here, and we just get 1 here, and finally we divide across by this bracket, so we get our result. So that's the integral done. We have to multiply by E over L. Well, that'll cancel the L on top, and we'll have an E going in on top, and finally we want to get I, the solution to our problem. So we'll have to multiply both sides by e to the minus RT over L. Don't forget we have a constant here from this integral. By the way, we have e over L times the constant of integration from this integral. But since e over L itself is a constant, we have e over L times the constant here. That gives us the constant which we call c. So the constant up here, which isn't written down, could have been plus d. And when we multiply, say we call it d, multiply d by e over L, we get another constant which we call c. Anyway, multiplying by e to the minus RT over L gives us our result. We cancel the exponential there.